Okay, so thanks everybody, and a really great pleasure to be here. Well, for me this afternoon, for many of you probably morning, evening, or night. So I'll have the pleasure to present you something about what we do on operational flood inundation prediction and monitoring at global scale using either modeling or satellite data. Now, before starting with the presentation, first maybe a couple of words to myself. So my name is Peter Salamon. I'm working at the Joint Research Center of the European Commission. I've been working there now for over 15 years, working around topics on flood risk management, mostly at the large scale. So we are looking at European or a global scale. I'm also coordinating the Copernicus Emergency Management Service, on which most of the products and the tools that I will present today is based on. So let me just give you a short outline of today's presentations. I've tried to divide it in three parts. So first we go and look how we do flood inundation prediction using a flood forecasting model. In our case, it's the Global Flood Awareness System of the Emergency Management Service. Then we move into from the forecast into the monitoring of a flood, and we do this also using another product of the Emergency Management Service as relatively new, called the Global Flood Monitoring. And the last part, I would like to show you a little bit a real world use case. And there we will look at relatively recent flooding occurring in Greece last year in September. And I'll show you a little bit the power of combining in the same kind of framework or environment, a seamless kind of information coming from prediction and then moving into monitoring of floods. Now I see, and by the way, obviously the work that I'm going to present is a work of many years and many colleagues, some of which are also present here today. So I'm just basically being the messenger here, but as you will see, there's lots of people that have been contributing to all this. Just a few words about the Copernicus Emergency Management Services. Some of you might not be familiar with this. So Copernicus program is Europe's Earth observation program. The most famous elements are the Sentinel satellites, but there are a number of operational services trying to provide value-added products based on satellite information coming from Sentinels, but also from model or in situ data. And one of the services is the Emergency Management Service, and as the name already says, I mean, we try to support all phases of disaster risk management. It's a fully operational service. It's already around for quite a while, since 2012. It's managed by the Joint Research Center. Most of the products are freely accessible, as also the ones that I will share here or show here today. You can see on the slide, actually, the service is quite complex. So we have an on-demand mapping component where users can activate, not only for floods, but also for forest fire or any kind of hazard, a rapid mapping or do look more at prevention when you do at risk and recovery mapping. We do also monitor and forecast droughts and forest fires. We have an exposure mapping component because impacts of hazards is clearly a key element as well. But today we'll focus on the flood element. So I will show you some of the products that are part of the flood early warning and monitoring component of the Emergency Management Service. So let's look first at the forecast. So we go on how do we do flood inundation prediction at a global scale. Now, in a nutshell, the methodology is outlined here in this slide. So we go from a relatively coarse scale distributed hydrological model setup that we use. We calibrate this like a traditional hydrological model, like many of you have done probably. We create with that a long-term discharge time series, in our case, more than 40 years. And we do a flood frequency analysis to derive return periods for each pixel in the model domain. Then we downscale this to our resolution that we want to use for the flood inundation mapping. In our case, this is 3 arcsecond or roughly 90 meters resolution. We derive design flood hydrographs, and then we do a lot of hundreds of thousands, actually small scale hydraulic simulations on this 90 meter resolution to come up with global scale flood hazard maps. And I will show you now in a bit more detail how this process works. So the distributed hydrological model that we use for this is an open source model. It's spatially distributed, called LISFlood. It's set up at 3 arc minutes, so roughly 5 kilometers at a global scale, and runs at a daily time step. In essence, basically, as I said, I'm showing you here the latest version of the GLOFAS version 4 setup. For those that know a little bit GLOFAS, we have a versioning system, and we regularly provide the system with minor or major upgrades. And this last setup, so the version 4, was just released mid last year. It's calibrated roughly around 2,000 gauges around the world. You can see them on the right-hand side. We also do parameter regionalization at ungauged locations. You can imagine for a global model, even though we have quite a few stations, there are also ungauged locations. And that setup we then use to derive a climatology, a discharge climatology from 1980 to 2022. And we use that to derive the return periods for each and every pixel individually in the model. Now, after that, as I said, we try to link this core scale model with the higher resolution digital elevation model and higher resolution stream flow network. In our case, we use the Merit DEM and Merit Hydro. I think most of you know those data sets already. So what we do is we create first virtual stations locations at the high resolution DEM, and then we create a lookup between the core scale GLOFAS grid and the high resolution virtual stations. And so it's a little bit schematized with the image on the right-hand side, where you can see how we do this. Then we, using the return periods from the core scale model, we create synthetic hydrographs that we then use to simulate, to do lots of small scale hydraulic simulations. So we end up with hundreds of thousands of small scale flood extent maps. An example is shown here on the slide as well, that we can, for different return period, and you can merge them either to create big global flood hazard maps, so for different return periods, or in our case, what we will do is create a flood event map by basically combining the GLOFAS forecast. So, and this is shown here on the left-hand side in step 1, where we run GLOFAS on a daily basis. We calculate the maximum or the medium of the ensemble forecast, link that in a similar way, like I shown before, to the high resolution DEM. And we don't run now the hydraulic simulations in real time every day, but what we do is we pick from the catalog or from the archive the relevant simulations that we have done offline to come up with an event-based flood inundation. And then, of course, we don't stop there. But I don't show this here in more detail, but we combine this, of course, with a lot of exposure information, because for most of our users, impact is, of course, relevant. So we use gridded population information or information from OpenStreetMap to kind of estimate the impacts. Now, I shall say that what we do here shouldn't be used for local emergency planning. This is a little bit different because this is typically done at like was shown by Maxim before, at the national or even at the regional scale. What we try to do with this approach is to have a first idea, an estimate of, in particular at the global scale, where large-scale floods or significant impacts are expected from a flooding event. Now, I have here a slide which shows a little bit all the methodology. Because of time, I have to keep it short. I'm also, I can of course share also then the relevant links in the chat if needed. Now everything is open, so also you can get the GLOFASS discharge climatology that I've been talking about on the climate data store. Also the hazard maps. I should just say that while in the GLOFASS we already use the new hazard maps, currently on the data catalog that I'm showing here, we still have the old ones available, but we hope within the next few weeks, if not 1 or 2 months, I'll update them, and then you'll have also the global flood hazard maps available, the most recent ones available. Now, let's move to from the forecast to the monitoring part. And this is done using, as you can imagine, satellite based. We do this using satellite information. We do this using basically Sentinel-1 synthetic aperture radar. I'll have in the next slide a few comments about why we do this. But basically, the idea was when we set up this satellite-based flood monitoring, we wanted to have a global and systematic monitoring of floods all around the world. We also wanted to have the information be available timeliness. You know that when it comes to flooding, time is of the essence. So having a product as soon as possible or as fast as possible is really crucial. So in order to meet those requests or these requirements, we have set up a fully automatic near real-time system that processes all Sentinel-1 data and provides the output within 8 hours of the data acquisition of the Sentinel-1 scene. There's a number of ways to access the data, as I will show later. We have also, because the satellite data allows a higher spatial resolution than the modeling, we have a 20-meter spatial resolution. And we also do this, we have processed also the full Sentinel-1 archive, so from 2015 to recent. Now, the advantages of such a system is that there's no time lost due to human intervention. As you might have remember, at the beginning, I showed that the emergency management service has also an on-demand mapping module, so where users can activate. This is here not necessary. Here, all the Sentinel-1 images, as I said, will be processed and analyzed for floods. Obviously that makes things quite a bit faster. As from experience, we have it that users typically only activate the service when the flood is already ongoing, and then you can imagine it's already a little bit late. This here is a clear plus of such an automatic system. We also discover quite a number of unreported events. If you do this at a global scale, you can imagine that not all of the floods are reported in the media. So also here, we hopefully are able to provide a more complete picture when it comes to the global scale on flood extent mapping. Of course, there are challenges to such a system, in particular false alarms. I will say a couple of words about this in the next couple of slides. And of course, it means that we process a lot of data, and the majority, luckily, doesn't have a flood in the Sentinel-1 scene. but it of course requires that we do this quite efficiently. Couple of words just on Sentinel-1, on which this system is based on. It's a synthetic aperture radar system. It's a 2-satellite system, Sentinel-1A and B. In theory, I say, because unfortunately, since December 2021, Sentinel-1B suffered an anomaly, and the data is not available anymore. There is, however, luckily a plan already for Sentinel-1C, hopefully in late 2024, that there will be a launch, so we'll be back again with a dual satellite constellation. Now, I will not go into details about how we do flood mapping using Sentinel-1 or SAR data. Just a very simple image. Basically, we look at the change to very low backscatter in the Sentinel-1 data in order to detect flooding. One peculiar item about how we do things is, of course, we need to be, because this is a fully automatic system, we need to have a high robustness of the system. Firstly, because as those that work with SAR data and do SAR-based flood mapping know that there's many water lookalike surfaces, like tarmac, like deserts, cropping harvests, etc. But there's also no sensitivity areas. So dense vegetation or urban areas are typically not, floods cannot be mapped using SAR data there. So in order to account for that, what we do is we use 3 different algorithms for Sentinel-1 based flood mapping. Those algorithms have been tested already quite widely and are published already in literature. One comes from the German Aerospace Center, looks at image classification with fuzzy logic and then region growing. We have a change detection algorithm from the Luxembourg Institute of Science and Technology, and a Bayesian classifier using the full per pixel Sentinel-1 signal history from the Technical University of Vienna. Now, you don't need to understand all the technical details. Key here is that all of the algorithms have advantages and disadvantages. And what we try to do with this ensemble is to, as I said before, to increase the robustness of the approach. So when 2 of the algorithms at least must agree for each of the pixels, and then you can see on the right-hand side, we denote this area as flooded. There's much more to talk about this also for the global flood monitoring. However, also here, I keep it short so you can read up on this. There's a paper published on a conference. We have really an extensive wiki on the global flood monitoring, including product user manuals, product definition document. We do annual quality assessment reports where we can show where it works and what works and what works less. There's a quick start guide for you to get going. And data access principally, as you will see also now in the use case, is through the GLOFASS map viewer. We also have a GFM portal where you then can download, make AOIs for the areas that you are interested in, download the products, and there's also an API access. Now, last but not least, I want to show you how combining those 2 elements and the power of doing this in one interface. And I do this using a recent real-world use case. As I said before, we will look at severe flooding in the Thessalia region in Greece that happened last year, so relevant recent. The flooding was caused by a storm called Daniel in the Mediterranean, lasted from 4 to 11 September. And I put here some key figures. So in the 7 days, between 400 and 1,000 millimeters of rain fell in this region of Thessalia in Greece. And for those that know Greece, which is typically a quite dry area, that's a lot of rain in a very short time period. widespread flooding started on 6 September and mostly affecting a very relatively small catchment, the Pineios River Basin, which is 9,500 square kilometers. And I highlight this because you know, if we look at this from the global perspective using, as I said, GLOFASS and the global flood monitoring tool. So 9,500 square kilometers in comparison to most of the river basins at global levels is very small. But so keep that in mind when I show you the results in the next couple of slides. The event caused well over 2 billion euros in damage and unfortunately also 17 casualties. Now, how did the GLOFASS prediction do, and how did we do the flood inundation mapping that I presented in the first part? On the right-hand side, you see two hydrographs, one from a forecast from 4 September for a relatively downstream part of the Pineios River already. Below you see the GLOFASS forecast for the day later. Now on the 4th of September, which is roughly lead time before the flooding started, 2 to 3 days. So it's not very long lead time, I have to say. You can see that overall there was a risk of flooding predicted, but the majority, let's say the highest percentage or the highest probability was not going beyond something that would be classified maybe as severe, so not going beyond a 20-year return period event, even though that some of the ensemble members, as you can see, went very extreme. Now that changed very dramatically one day after, where you can see that there, in particular for the 7th of September, the highest probability for all the ensemble forecasts exceeded well the 100-year return period event. So with relatively short lead time, the prediction already indicated that this could be quite a severe event. On the left-hand side, you see a screenshot also from the GLOFASS map viewer. The blue is the event-based flood inundation map that was derived, as I described in the first part, from the most recent GLOFASS prediction. And then you see in red, that's the administrative region of Thessalia. So where we aggregate the impact information at administrative region to indicate that in this region there could be something severe happening. Okay, now let's look at how this event developed from a flood monitoring point of view. And this is again screenshots from the GLOFASS map viewer. So you can, in the GLOFASS map viewer, you can activate all these different layers and overlay them so that you can really have a seamless experience, let's say, as I said, going from forecasting to monitoring. On the left-hand side, you see a Sentinel-1 acquisition done 6 September in the morning. So you see already the little purple spots are flooded areas. There's not really a lot visible at that point in time. The red lines are the stripes of the Sentinel-1 acquisition. But then if you look just roughly a day later, on the 7th of September, in the afternoon, the large-scale flooding, as you can clearly see, was already ongoing. And here we are talking about very large areas, hundreds of square kilometers being flooded. Now, I show you here, I've overlaid here, and you can do that also in the GLOFASS map viewer, the flood inundation coming from the prediction and with the one that is observed on the 7th of September. And you can see that the match is overall reasonable. Clearly, we have to acknowledge that this is coming from a forecast. And it looks at the maximum flood extent within the forecast, whereas the monitoring is just a screenshot of the moment, kind of that situation in the afternoon on the 7th. But overall, the match is decent. There are some over and some underestimations, but pretty much we have roughly captured the magnitude of the event. Just for the sake of completeness, the next acquisition from Sentinel-1 were done on the 12th, and on the 13th of September here, you can see that even almost 1 week after the flood started, very large areas were still being flooded. So the water took quite a while to retreat, which was of course also causing a lot of problems to the local communities and to the region here. So this is just an example of you know, combining forecast and monitoring information in the same framework, so that you can really provide to your users let's say the complete experience and during an event. I'll stop here. One thing I want to mention before closing. If you want to find out more about GLOFASS and the GFM, we have regular annual meetings as well. The next one will happen just in 2 weeks, 5th, 6th of March, will be fully online as well. So you are still in time to register. I can share also the link in the chat if that's wanted. And there's also more info and a draft agenda on the GLOFASS webpage in the news. You can find all information there. So thanks a lot for your attention, and I'll stop here and hand